to the second part. So, molecules. So here are a few keywords. I don't know if you should remember them or not, but just to have them. First of all, a linear combination of atomic orbitals, or LCAO. This is one more approximation of the approximation that talks about quantum superposition of atomic orbitals and technique to calculate molecular orbitals in quantum chemistry. I will show you a few examples of that because it's mainly the topic of this second lecture. And the second thing, the valence shell electron pair repulsion theory. So this is the model that tells you that if you have pairs of electrons in the valence shell, well, they are negatively charged. So what do you expect from like-charged particles? Of course, they will repel. And this effect will give us some insights into the form of the orbitals and how they are situated in the 3D space. So that may be, let's say, interesting for you. Okay, now let's get to so-called molecular orbitals. And we try to do something in that approximation and maybe get some insights how everything works. So here is an example of two hydrogen atoms. Each hydrogen atom has one electron sitting on its 1s orbital. So here is hydrogen atom number 1, here is hydrogen atom number 2. For each of these electrons, I can, I don't know, draw or calculate somehow its psi function. And now let's think what happens if I bring these two atoms together. So here is one hydrogen atom, here's another one hydrogen atom. It's crucial that they have spin. One has spin up, the other has spin down, but we will get to that in a moment. Think of it in such a way. So this thing is, let's say, vibrating somehow. And here is some psi function, so something again is vibrating. If I bring them close together, I can have some interference pattern that can be constructive or can be destructive. This is schematic view just of constructive and destructive. So if you want to draw for S, it may be better to draw like this. So one is like this, and the other one is, I know, like this. If they interfere constructively, they create one new molecular orbital. So here it is. Here's how it looks like, this molecular orbital. So this is some sort of distribution of the probability. You have large probability to find electron near the atoms and small probability to find it somewhere else. And they may interfere destructively. So the like this and like this. And here you have the so-called anti-bonding orbital. Once again, this is the idea of linear combination of the atomic orbitals. So I have one atomic orbital, I have another atomic orbital. I am trying to combine them. Of course, I can combine them in different ways. You may tell me that we may have a different phase shift. It's not only constructive and destructive and so on, and that's true. But it turns out that if you calculate the energy of that all possible interferences, the constructive interference gets the lowest energy. And the lowest energy has a tendency to be populated with electrons. So it's the first level that will be populated with electrons. So take a look. So here I have atom number 1. It somehow wobbles. And I have atom number 2 that wobbles intact. So they are interfering constructively, and at the end of the day, you expect something. Bad color choice. Well, something like this. I don't know. So you have higher probability to find electrons between the atoms. In that case, they are screened. They interact with positive charges, and basically the energy of the system is the lowest. So that's okay. Now let's check another case. What if they interfere this way? So this goes up and this goes down. So you see that there is a part that they are trying to compensate their wave functions, and you get lower probability of getting electrons there. So you have some higher probability here, it goes down here, and once again it goes wave function goes down here and probability goes up. So that's why you get these two lobes, and they represent so-called anti-bonding molecular orbital. Okay, what's of that? The thing is, when atoms come into contact and they create some chemical bond, new molecular orbitals are created. The number of created molecular orbitals is the same as the number of atomic orbitals that took part in that interaction. So I have two orbitals coming into this interaction, I have two molecular orbitals formed. What does it give to me? You see that this orbital has lower energy than each of the 1s orbitals originally had. This means that if you bring together two hydrogen atoms, they want to be together, because this way they minimize the energy. So that's what we have. Now think, the anti-bonding orbital has a higher energy than originally 1s atomic orbitals had. So if this were not hydrogen, but let's say helium atoms, what would happen? I need to place now not 2 but 4 electrons on 2 molecular orbitals. And there is no other way than placing 2 electrons on the bonding orbitals and bonding orbital and 2 electrons on the anti-bonding orbital. And here is the thing. So how much energy I gain by placing these electrons on the orbital with the lower energy, the same amount I lose when I place 2 another electrons on the anti-bonding orbital. So now tell me, do you see now why helium is a noble gas and exists in a form of an atom? So you don't see helium-2, you see helium. But hydrogen exists in a molecular form. So you see hydrogen H2, but you rarely see atomic hydrogen. So is it clear?
Because only one bonding orbital can be formed, and the other 2 electrons have no choice but to create anti-bonding orbitals.
Yeah, they have no choice but to go to the anti-bonding orbital. So orbitals are created instantly. They depend just on the potential, but when you spread electrons on them, you have no choice but to put 2 electrons here, and you lose in energy so much as you gain in energy here. So that's it. Okay, this part shows you that we can promote electrons between that orbitals as we did for atoms by adding some energy. So by shining some light, we can promote electron from bonding orbital to the anti-bonding orbital, one of the 2 electrons, that's for hydrogen. And how do you think, what happens? What is this picture representing?
Ionization.
No, ionization will mean that electron just goes away. It stays within
So
the molecule.
an
But
excitation like in ion, basically in neon lights, you
uh,
excite an atom to go in
yes,
higher level.
but now you see that you have one electron on bonding orbital, one on the anti-bonding orbital. So this construction has is no better in energy as two separate hydrogen atoms. Same thing as for helium, but helium carried two electrons. Each of the atoms carried two electrons, and we were forced to spread four electrons between bonding and anti-bonding orbital, and how much we gain, so much we lose. And here is the same case, but we have forcefully promoted one electron to the anti-bonding orbital. So this is basically splitting a molecule by shining some light on that molecule. Um, yes, that's correct. H2
So
goes to H plus H. Okay, here is one more slide. So it's just terminology. So what do we call a bond length? So you see that there is some optimal distance between the nuclei that leads to maximum stability. And once again, it should be calculated by some sort of complicated equations. We don't go into that, but it shouldn't be strange for you that bringing them too close makes kernels repel as positively charged, and keeping them too far away basically makes nothing because they do not interact. So there is some preferable distance, and we call that a bond length. Um, okay, here we go again about bonding and anti-bonding orbitals. Uh, the thing is that we will be interested in that orbitals because they basically make all the chemistry that we are working with. So here's once again our bonding and anti-bonding orbitals. We call them sigma bond and sigma star for the anti-bonding. So everything anti-bonding will get a star here. Here, how do they look like? Uh, okay. Uh, what about uh, p orbitals? So here we have p orbitals, and we can ask ourselves how can they overlap? And here is an example how to overlap two p orbitals, and you see that once again they can combine in phase. Is the image down here, and we are creating so-called bonding orbital. So it's called p sigma orbital, uh, and here we have an anti-bonding orbital by combining them in different phases. So phase plus, phase minus, and you see that here we create some sort of nodal plane, and this is an anti-bonding orbital. So depending on how orbitals interact, we will get bonding orbitals. We will get anti-bonding orbitals. We can combine them sideways. That's one more interesting trick. Once again, we can create something binding and something anti-binding. This time we call them pi pi bonds. We will often see pi bonds when we will talk about, I don't know, some alkenes or alkynes. So if we have some double bonds, triple bonds of bonds, some of them will be pi bonds, and we need to get to that. Uh, here is one more example of the effects that we will carry about. It's called an inductive effect. It's a shifting of electrons in a sigma bond in response to the electronegativity of nearby atoms. So here you see two examples. So one is methanol. We know that oxygen is pretty electronegative, and it tries to pull electrons for himself. So you see here this red blob. It means that there is much higher probability to find electron there than somewhere else. Here is another case. This is methyl lithium, and you see that lithium in this case is trying to give away his electron. So basically, he's positively charged, and he gives his electron into the to methyl. So you see minus charge on carbon atom and plus charge on lithium atom. These images are often drawn with this sort of arrows. Arrow shows in the direction of the negative charge, and it often has the thing that reminds plus and tells you that the other end of the arrow is basically plus charge. Okay, now you should just a reminder for you that molecular orbitals are created from atomic orbitals, and you should think of them as the new coordinate system that allows you expressing any quantum state. If you choose that carefully, electrons would like to remain in that pure state, so you will have just a convenient convenient way of describing your system. One more thing, orbitals with close energy interact effectively. So if you want your orbitals to effectively interact, you better make sure that they have similar energies. And here is one more classical analogy for you. It's the effect of a resonance. Here you see no resonance. So 520 Hertz has a tuning fork, and the other tuning fork, it does not respond. So you may think of it like if you had some wave function, it was wobbling, and the other wave function was wobbling with pretty different frequency. They will not interact effectively. What if they interact effectively? Here are close tuned. Look at the ball. So you see that tuning force.
Like because
Yes, please.
like because we put the same amount of energy that's resonance that must have.
They have the same internal frequency, so they can effectively interact. So if you think about two waves, if they have very different frequency and you add them together, you get some mess out of it. So nothing interesting comes out. If you have waves with close wavelength, you will see that effects that we were discussing. So they will interact constructively, destructively, and so on. This is just a classical analogy to show you that in a classical world we have effects that may depend on the internal, let's say, in internal parameters of the system, and if you have very close wavelength, they will effectively interact. So this is some sort of analogy of effective interaction. So that's why you should not expect electrons with a very different energy level to interact effectively, because their wave functions will have pretty different parameters. So that's it. Okay, so a little bit more about electronegativity. So here is an example. How can we understand that in terms of atomic orbitals, and what does it bring to us in terms of chemistry? So here are atomic orbitals for carbon atom, for oxygen atom, and for fluorine atom. And if I measure energy from the energy of ionization, so these are filled electron shells, so electron shells that contain some electrons. Of course, I can draw them more up to the 0, but it has no sense because they do not contain any electrons, so they are not interesting for us. And I can measure the energy I need to remove an electron and make it free. And you see that different atoms have different ionization energy that I need to put in to get an electron out. What does it mean? That this is a scale I can compare different atoms. Let's compare sodium atom and fluorine atom. Sodium atom has 3s orbital with 1 electron that will take part in different chemical stuff, and fluorine has 2p orbital with 1 electron that will basically do the thing. And when they combine, when they overlap, It turns out that new levels that are created, so the bonding orbital is very close to in energy to the fluorine orbital, and the anti-bonding is very close to the sodium orbital. And this electron is basically transferred to the 2p orbital of the fluorine. So it's basically starts belonging almost exclusively to the fluorine. And you have and that means that if you have, I don't know, some sort of solution or something like that, you will not get sodium fluoride, but you will get sodium ion and fluoride ion that will do something on their own. We will meet this in some reactions, so probably I'll tell you more about it. One more table to compare different characteristics. So for example, if you have atomic orbitals that have the same energy, when atoms come into contact, two molecular orbitals are created. You see that here is one bonding and anti-bonding molecular orbital. And if you break this chemical bond, it is quite probable that you will get whatever we had in the beginning. Well, we will call that later radicals because they have these electrons, but anyway. So it's called, of course, this is called homolytic fission. Of course, there is some probability of getting heterolytic fission when two electrons will go with B or with A, with pretty equal probability. But anyway, that's that's what we have. Now what happens if the atomic orbital on B is a little lower in energy than atomic orbital on atom A? Now you see that the energy of this molecular orbital is closer to the atomic orbital on B, and if we break this chemical into parts, it is more probable, it is easier to break them, so that both electrons will go to B. Because in that case, I will need to lift them up by a smaller amount of energy. So it is quite probable that you will get B minus and A plus. And if energy of atom B is a lot lower than atomic orbital on the atom A, you get the bonding orbital that is almost the same as the orbital of atom B, and you get anti-bonding orbital that is almost the same as atom A. And this compound most probably will exist as ions. Who can tell me who will get minus and who will get plus? A or B? So A on this side, B on this side.
It's gonna be B on the
So
no, like down
B will
because it's
get
plus minus.
So B will get both electrons. Yes.
Yeah, because we don't have minus there.
So his orbital is much closer to the bonding orbitals to the bonding orbital where electrons already live, and I don't need to spend so much energy to make this electron so high. So I don't need that. I just let B atom to keep them both. So B atom becomes minus, and this atom now loses his electron and becomes plus. Okay. One more thing to notice, that bonding, that there is basically a continuum in bonding from covalent to ionic, and that's just a result of unequal distribution of bonding electrons between atoms. We use lowercase Greek delta. I showed it to you already, which means some sort of partial charge, and you may see here a picture where we have a totally covalent bond, so they are not charged, both electrons are equally used by both atoms, Here y is more electronegative than x, so he tries to keep these electrons closer. So we have partial plus charge on x and partial minus charge on y, because electrons spend more time near y than near x. And here is ionic bond. So that's what I showed you on the last slide. When y is quite electronegative and it keeps electrons for himself. Okay, what's this? This is one more type of bond. This is a pi bond. So here is pi bond. It is covalent, but there is also some sort of electrostatic interaction to that if you have a pi bond to some electronegative atom. So here's an example of pi bond between two Th atoms, and between two carbon atoms, and between carbon atom and oxygen. So you can still have pi bonds between carbon and oxygen. And if we calculate some sort of energies, I'm not sure, I don't see on my own the numbers I wrote there. Let me make this smaller. I can tell you the numbers. So this is basically an experimental fact that shows you that charges, they matter. So if we have CO bond, it is 725 to 760 kilojoule per mole, while CC bond has 600 to 625 kilojoule per mole. So basically we have some higher energy, so this bond is more energetic, and that's because oxygen is more electronegative and tries to keep electrons for himself, and we have some additional electrostatic interaction. Okay, let me check, where are we? Good. Good. Okay. Here is one more example of the overlap when we create a pi bond. So efficient overlap can be if we have p orbitals of well, approximately the same size, which means the same principal quantum number n, and you see how they should be, how their geometry should look like in the 3D space. So if they are different in size, we have, well, not so efficient overlap. It can be quite inefficient. And you see that you cannot overlap them sideways. So if you try to overlap two p orbitals sideways, it doesn't work. So they do not overlap well. If you think for a while, I guess you can guess why it's so. But you can effectively overlap p and s orbital. That's pretty okay. So you can do that, and we will see appropriate bonds. And here we come to the hybridization. I guess it's the thing you were asking me about, that sort of infinity sign. This is an experimental fact that if you consider, for example, methane, it has four equal bonds, equal in strength, equal in their length. Here it is. And of course we had the question, why is it so? Because we should have one s orbital that is quite different from other three p orbitals. And it turns out that there is such thing as a hybridization. I guess it was predicted by Linus Pauling. And here I have some visualization for you, but I don't remember what it was on my own. So let's check. What do I have here for you? This is methane, and here we can look for sp3 hybridized orbitals. Let me turn them on. Okay. well, doesn't look pretty interesting, but anyway. So these are hybridized, 4 different hybridized orbitals. Maybe the image was even better. Okay. So if you think for a while, you can, I guess you can get the idea how do we get this. So for example, here is s orbital. So this thing is some sort of one phase. Let me draw it like this. And here is our p orbital. We get something, I guess, like this. So one half wave, the other half wave. Of course, this is some sort of classical analogy, so take it with a grain of salt. But anyway, you see that there is a part that wave functions are compensating each other, so we have destructive interference. With that destructive interference, you get this small tail. And there is a part where you get constructive interference, and this is this part. This large lobe is basically a result of the constructive interference. So if you think for a while, I guess it would be easy to understand. Okay, so here's one more example. So we have a few molecules, and with these images, I want you to see that some atoms have electron pairs that are non-bonding electron pairs, and we should take them into account. So here is methane, so all electrons are used to make bonds, but here is nitrogen. It creates just 3 bonds, but it has 1 electron pair that is not used in any bonding, but these bonds, they still feel some electric repulsion from this orbital, and that's why you have something that looks like tetrahedral. And the same thing for oxygen. But here we have 2 non-bonding electron pairs, and you can see that once again they are repelling each other. Remember, at the beginning of the lecture I told you that electrons on the valence shell, they are trying to repel each other. So here it is. So this pair tries to repel all these pairs. So each of these lines is basically a pair of electrons, and they are trying to repel each other. Okay, here is one more thing for you to play. I hope that it works, that it still works. Okay. And how do I switch to... here it is. Great. So here is some sort of tool that approximates 3D views of the molecules, and I think you may want to play around with it to gain some insights of what is happening with that molecules. So let me try to build something. I guess. Okay, I'll remove everything. Let's make just a methane. So here you see methane, and you can guess that electron pairs that constitute these bonds, they are doing everything they can to stay as far apart as they can. And it turns out that this tetrahedral structure is the best way to stay apart. If instead of the carbon atom I will use nitrogen atom, you see once again that they are trying to stay in some sort of pyramidal shape. And the reason is that here is one invisible electron pair. This software does not show it, but it is there. If there were no electron pair here, if, I don't know, it somehow miraculously disappears, what kind of structure do you expect?
Like a planary structure
Yes.
without like any angle.
Absolutely correct. That would be a planar structure, so just nitrogen atom, and 120 degrees, 3 H atoms. So that's what you will get if this electron pair somehow miraculously disappears. Probably it won't, but that's what we have. So you can play around with this demo, you can try some more complicated molecules, and I think that may gain you some insights in the molecular structure. How do they look like, and why do they look like the way they do, and so on. Okay. Now let's get back to our slides. Okay, so what's this? Now it's time to talk about double and triple bonds. Here is an example of creating a double bond between two carbon atoms. So we will see that a lot. Let me find. Here it is. So let's take a look how it is created. So how do we create a double bond? First of all, we have a sigma bond here that is created from these two molecular or from these two atomic orbitals. They combine and give you this sort of molecular orbital. This is a sigma bond. So they have combined and they created a new orbital. Okay. Now this lobe and this lobe, they interact in a sideways. So I showed you on the previous slide that they interact sideways, and they create as binding orbital something like this. This is called pi bond. So this is pi bond. That was sigma bond. This is pi bond. So this is how they interact. The interesting thing that to interact effectively, they need to keep up their p nature. So these orbitals stop taking part in the hybridization. So if you see a double bond, it means that one of the p orbitals went into this double bond without distorting its p nature. About the rest, three orbitals, 1s and two other p orbitals, let's say px and py, they still hybridize, and they still create some sort of mixture. So everything except this one that went to make this pi bond. Okay, one more link. Let's check out what do I have here. So here's an example of a molecule, and this is I think let's show pi orbital. So here you see orbital for pi bond. So here it is. It's two p orbitals that were combined in phase and created bonding orbital. So that's it. Okay, let's show you what do we have here. Let's show you sp3. So these are the orbitals that were hybridized. So they have hybridized and they look pretty the same. So this is one s orbital and two p orbitals. So this is sp2. So here it is. Okay. I guess I should have somewhere triple bond. Yes. Can you guess what happens in the case of the triple bond?
A sum of orbitals canceling each other also interact spatially?
You see
I
here
don't
is
really know.
Like we'll have one more orbit that continue and calculate with them.
let's check this image. Do you see we have two pi bonds. So this is say so this and this is one pi bond, and that thing over there, and this is a second pi bond. So we have two pi bonds. We have one sigma bond. Here it is, one sigma bond. These pi bonds were created with p orbitals, and these p orbitals, to effectively overlap, they do not want to lose their p nature. So these two orbitals are basically taken out of the hybridization. So they will be not hybridized. You can see the picture right here. So I have two orbitals, py. It creates me this pi. Not this pi bond. This bluish pi bond, y orbital. I have pz that creates me the other pi bond. They keep their p nature. What is left is one s orbital and one p orbital, and they will be hybridized to give two sp orbitals. So I guess you get the idea. So if we have carbon atom that has only single bonds, everything is hybridized. So you have one s, 3p orbitals hybridized, so you get sp3 hybridization. If you have a double bond, it means that one p orbital was taken from the hybridization away. So what is left is one s and two p orbitals. So you get sp2 hybridization. If you have a triple bond, you have now two additional bonds, which means that two p orbitals were taken away from the hybridization, which means that what is left is one s orbital and one p orbital, and they are hybridized into sp orbitals. So I hope it's more or less intuitive for you. So we can look at additional bonds, and then you consider how many p orbitals were taken away from the hybridization. Okay, I guess here are a few examples for you to make this, I don't know, maybe more intuitive. So here is a carbon-oxygen bonding. Once again, we have double bond. We will meet these double bonds in a lot of places, for example, in ketones, in acids, and so on and so forth. So pretty common structure. And you have this double bond. You have oxygen atom. So please look at this in the 3D. So this pi bond is created with two p orbitals. So here is p orbital from carbon atom, p orbital from oxygen atom. They overlapped, created this pi bond. Everything else went into the hybridization. So lone electron pairs are undergoing hybridization as well. So you have now what? You have one p orbital taken away from hybridization, so you get s and two p orbitals. So sp2 hybridization. sp2 hybridization for oxygen, sp2 hybridization for carbon atom. That's what we have. Okay, here is one more view. So carbon-carbon sigma bond between sp2 orbitals on carbon and nitrogen. So here we have once again. So we have carbon atom, we have double bond, we have nitrogen, we have lone electron pair on the nitrogen, and here how it looks like. Interesting thing for you to notice. In 3D, when we have this pi bond, it basically does not want, it basically repels these bonds. So these other bonds are repelled. So they tend to stay in the plane. And if we look now, let me return to that demo I showed you. Or no, it was where was it? No. Here it was. So let's return to this demo. And let me create, or wait, let's go with this. Why not? So here we have some carbon skeleton. You see how it looks like. So you see these angles. These are basically angles like in that pyramid. And let me add somewhere here a double bond. So let me add a double. Let's do this one. So let it calculate for a while. And here we have it. So please take a look. We have double bond. It does not show us, but there are, let me turn it this way. But there were, oh, I'm drawing black on black. Yes, quite smart. So there were two p orbitals. They have overlapped and created pi bond. This pi bond contains some electron density, so it doesn't want other electrons to be close, somewhere close. And you see how this structure became flat. So I hope you see that this hydrogen, this carbon, and that carbon, and this hydrogen, so they are all in some plane. So here it is.
It's
Okay.
because of the like hybridization.
Because of repelling from the pi bond. And hybridization gives us the fact that these bonds, this one and there is one sigma bond here, that they are the same basically. Okay, so I hope you can see that how this thing flattened when I just added a double bond. If I change that back, no, if I change that back to a single bond, let it recalculate, and you see once again that there is no such plane anymore. Okay, I'll leave it that in the back, maybe. Maybe we'll use it once more later. Okay. Let me check one moment. How much time do we have?
About
We have up to 20 minutes.
I feel like about half an hour.
Okay, so
8:50 at the end of the pair.
Okay, I think we can manage that. Yeah, so just a glimpse on this slide. I I don't think I will spend much more time on that. I think you can grasp that on your own. It's pretty simple. Just play around with that demo. You can look at the 3D structures. They basically they influence the chemistry of the molecules we know. And here is just some sort of demo of how do these molecules hybridize. So once again, you see a trigonal planar sp2 carbon atom. You see the same thing between carbon atom and oxygen atom. Once again, oxygen can be sp2 hybridized. Here you see how do orbitals overlap for atoms that have different hybridization, because all my previous examples contained the same hybridization. Here is an example when they do not. So here is a methyl group. This carbon atom is sp3 hybridized. So and this is another carbon atom. This is a part of the carbonyl group, and it is sp2 hybridized because it has double bond to oxygen, and this double bond consumed one of the p orbitals, and it does not take part in the hybridization. So we can connect carbon atoms with different hybridizations. That's pretty okay. Aceton nitrile, the same example. We have methyl group here. Carbon atom is sp3 hybridized. This is methyl group. We have sigma bond to the carbon atom that is basically sp hybridized because it has a triple bond, and this triple bond consumes two pi orbitals, two p orbitals, and only one s and one p orbital take a part in the hybridization. And here is sigma bond to n. N is sp hybridized with a lone pair. Yes, I see question.
Yeah, you said 2 pairs of p or 3 pairs.
Um,
I think it's 3, but it can be.
where do should I look?
You mentioned about when we have like 3 pairs of like p3 in the lines of 3 line of p. So you mentioned just
this
2p,
example,
so
yeah.
just I'm asking. Yeah, you
This
just said
example.
2 of them, so I just ask 2 or 3.
Look at this picture. So we have two pi bonds. They are created with the help of p orbitals. So here is one p orbital. Here is another p orbital. They are consumed with pi bonds. So only two of them. The third bond is a
Okay.
sigma bond. So you see, it's a sigma bond. This one. And
Yeah.
in sigma bond, a hybridized orbital takes part. Okay. What this? Here is an example of filling atomic orbitals for on N2 for the nitrogen gas we breathe. Well, we don't breathe it, but we have it enough in air. And here I just wanted to show you that all orbitals that these atoms have, they can be thought as creating some sort of atomic orbitals, but you see that the lower levels, they they are filled. This means that you will have bonding and anti-bonding orbitals in the molecule filled with electrons, and they will cancel out. So that is the reason why we will mostly consider only the higher energy orbitals with the electrons that we call valence electrons, and only they will take part in some sort of chemical reactions. So the reason is simple. You can still consider some lower electrons and calculate some molecular orbitals for them and so on, but at the end of the day you will come to the state when when all bonding and anti-bonding orbitals are filled up, and whatever you gain on filling bonding orbital you lose on filling anti-bonding orbital, so they basically don't influence on anything. So it's just in case you will ever wonder why do we consider some electrons but we neglect another. So That's the reason. And this slide shows you another thing. This is the reason why are we concerned with all that bonding, anti-bonding, and all that orbitals. You see that if we consider a chemical reaction, so here is a simple chemical reaction, so a borohydride yes, and this chemical, and what we have a filled non-bonding sp3 orbital of the nitrogen. It has 2 electrons, and we have empty p orbital of boron. And we can expect that if these molecules come together, these electrons will be placed on the appropriate atomic orbital. So here is the scheme. We have once again, we will have some bonding orbital and some anti-bonding orbital, and if you place both electrons on the bonding orbital, we gain something in energy, which means that this chemical compound will be stable and would like to exist as that new compound. Okay, but what about orbitals and their geometry? You see here that this collision will give you effective result. I mean, if you collide these 2 molecules, you will get your chemical reaction. But if you collide them somehow sideways, so here are examples of different collisions that are not productive. So they do not lead to any chemical reaction. And that may mean something in different cases. So for example, if you calculate energies, you will see that some reaction can go. So it's much better for the chemicals to combine and give you something. But in practice, you will see that there is some sort of so-called steric hindrance, so that you cannot position your orbital so well for the reaction to go, and you will not get that reaction in the experiment. Despite the fact that if you calculate just bare energy, you will see that yeah, that's good, it should go. No, it will not, because some sort of geometry stays in your way and does not allow you to perform that reaction and to get some productive collision that will put orbitals in appropriate position to overlap and to perform all that chemistry. So for in the future, we will study mechanisms of the reactions. I will show you some of them. And for the reaction to take place, molecules must first overcome their electronic repulsion by charge interaction and or orbital overlap. They should have orbitals of appropriate energy. So you remember the example with the ball and 2 tuning forks. If you have orbitals of very different energy, you have very different frequency in that orbitals, and they do not interact effectively. So you should have them more or less close in energy, and they should approach each other so that these orbitals can overlap and form a bonding interaction. So that's what we should have. And here are some examples that they are once again reiterating what we saw previously. One more interesting thing, conjugated bonds. Sometimes what we draw does not perfectly reflect of what we have in practice. So here is a butadiene. So by the name of diene, you should guess that we will have 2 double bonds, and here is its chemical formula. The thing is that if you look at the butadiene, you might guess that we will have p orbitals of carbon atoms interacting with each other. They will overlap somehow and create some pi bonds. We draw them as double bond here and double bond here. But the thing is that basically this carbon with its p orbital interacts with this one as well. So conjugation is something more than just having 2 bonds. And here is an example of different molecular orbitals that we get in a conjugated system. So a bonding orbital, everything is in phase, all 4 carbon atoms, so not just considering them in pairs. Here you see how that looks like and how do we fill them with electrons. And here are some less efficient interactions when something is in phase, something is out of phase. So it turns out that the next next molecular orbital in energy is when you have these two in phase and these two in phase, but as pairs they are out of tune. So here it is. And the next orbitals, some different combinations. We have 4 electrons to put there, and you see how do we put them. So 2 electrons here, 2 electrons here. Okay. You see this terminology like HOMO and LUMO. You will probably meet them later. One of them is the highest occupied molecular orbital, so it's the highest molecular orbital that contains at least 1 electron. And LUMO is the lowest unoccupied molecular orbital that contains no electrons. Once again, you can check out these ideas about nodal planes, so when we combine in phase, out of phase, and so on. So I'll leave that to you. What I want to show you, an interesting thing, probably, that if we have that sort of conjugated bond and that sort of interaction, it is energetically favorable. So here is orbital of ethane. So it has 1 double bond, and you see the distance between HOMO and LUMO. The thing is that if some chemical has, I don't know, some color, that color is connected to the energy gap between HOMO and LUMO. So that basically defines the color of whatever you have. This gap is quite large. It corresponds to the light. Oh, I see a question. Yes, please.
It is the same light that we can compare when we talk about stars, about the light of the stars.
I see. Well, I don't think that such complex chemicals can exist at that conditions, but the idea is pretty the same. So you have energy levels and you have electrons moving up and down, and they can either absorb some light or they can emit some light. And that light, it depends on the energy gap. It has more to do with atomic gases, maybe I don't know, hydrogen gas or helium and so on. That was on the slide I showed you in the first lecture. So there were that lines, spectroscopic lines. But you see that we can have this thing in some more complicated chemicals. And what I want to show you that orbitals of butadiene has much smaller gap between HOMO and LUMO. It's much nearer ultraviolet light. So here we see some sort of scale. Here is ultraviolet and here is visible light. And it turns out if we add many such double bonds intermingled with single bonds, these systems will be conjugated, and we can make the energy of that transition to get into the visible light. So for example, lycopene, red pigment in tomatoes, it is red because it has many conjugated bonds. So they basically made that that gap so small that we can see it as some sort of color. Lutein, a yellow pigment of egg yolks. Once again, you see this pattern of many conjugated bonds. Beta-carotene, an orange pigment in carrots. The same thing. Here you see some small table that shows you what happens when you conjugate more and more bonds. It turns out that it's really hard to get blue or green polyenes, so you should get some different mechanism, and I hope that I will have time to tell you about aromaticity that brings that. But you see that depending on the length of the chain, you can get different colors. That's because we are changing that gap. Here is the case with much more complicated chemicals. Here is a green pigment created. So you see here many these rings. I will tell you about them in a moment. But I don't want you to to get into details of these reactions. But what I want you to show is a really nice tiny demo. If you have sunflower seeds, they contain that sort of chemicals that we can transform into the chlorogenic acid in basic conditions. Let me show you here. Here it is. So you see that aeration and basic conditions. And this is a green pigment. And what's interesting, and you can probably make that at home, you can take sunflower seeds, and I have just boiled them in water on a pan with addition of some sort of sodium hydrocarbonate. So added sodium hydrocarbonate that makes conditions a little bit more basic. I have boiled that and then left it overnight to dry on air. And you see that as a result I got this green sunflower seeds. So this is photo taken from my Facebook account. So this is my hand and this is sunflower seeds. Yes, please.
So is it basically we can say because we like lower the pH. So we have some pH in the seeds and we lower the pH and that's why they change the color.
Because we lowered the pH and we had excess of oxygen, there was a new chemical created called chlorogenic acid. It contains many rings, and you can see in here. So these green pigments, they contain, you see, many double bonds. So a lot of things are going on here, some sort of conjugation and aromaticity and so on and so forth. And all the things, when you make electrons like smear all over the molecule, it makes the gap smaller. So smaller gap between the highest occupied orbital and the lowest unoccupied orbital. So basically that was some sort of chemical synthesized in that sunflower seeds, and that chemical is able basically to absorb some light and reflect some different, and it looks like this. So it's pretty green. As I remember, inside they were green as well, and they are pretty edible, so you can make that at home and try it. So it shouldn't be something quite complicated. Okay. I guess this is the last part of what I wanted to show you today. Everyone's pretty tired, but let's do it. The last topic is aromaticity. So aromaticity, it's one more effect that looks like that sort of conjugation, and that makes our molecules a little bit more stable. So here we have some sort of plot that shows different energies. Here is cyclooctene. It contains 8 carbon atoms and 1 double bond. Well, if we hydrogenate it, so it means that I will react it with hydrogen and transform it into cyclooctane, so no double bonds. I can measure some difference in energies. So this double bond basically has some energy. I will expect that if I add 4 such double bonds, I will have this difference in energy 4 times bigger than I had with creating just 1 double bond. Because basically this energy of hydrogenation is the energy of destroying of double bond, or you can think of it as the energy of the double bond, so how tightly it keeps atoms together. So 96 times 4 is something around 410. Of course, it's not equal, but close enough. Now look at another case. Here I have a cyclohexane, and I perform hydrogenation once again. So I have some difference in energy, 120 kilojoule per mole. So one bond should cost 120 kilojoule per mole. If I create 3 such bonds, I would expect 360 kilojoule per mole, so somewhere near here. But I see that this energy is quite different. It is something like 208 kilojoule per mole. And this means that something happened to energy. So this molecule is, for some reason, more stable than I expect it to be. And the reason is aromaticity. Once again, benzene has 6 pi molecular orbitals. So here you see how these p orbitals of carbon atoms can interact to create that new pi orbitals. Here you see the lowest orbital. They all overlap in phase. Here it is, the lowest one. Then we have 2 more orbitals like this and like this. And then we have 2 more orbitals that are empty in this case, like this and like this. And 1 more orbital when everyone is out of phase. It has the highest energy. You see that only the lowest molecular orbitals are filled with electrons, and it turns out that in this case we have pretty decent delta in energy. So this chemical should be much more stable than we expect. So here's once again how these orbitals looks like. You can look at it for a while and think about all these overlaps, in phase, out of phase, constructively, destructively interfering. So you can look at that and get some idea how that looks like. And you see that these pi orbitals, here is the dashed line that represents energy of an isolated p orbital, and all orbitals below, they are bonding orbitals. So basically we put electrons here and we get some gain in energy. This is a quantum mechanical effect, and I'm afraid I don't have some perfect explanation of what is happening, because that will need to calculate once again Schrödinger equation and so on. But we have some simple rules that can help us to spot such chemicals and understand that there's something will happen interesting. It calls Huckel's rule. So planar, fully conjugated monocyclic systems with 4n plus 2 pi electrons. Benzene has 6 pi electrons. It's 4 times 1 plus 2. The next one will be 4 times 2 plus 2, that's 10 electrons. They have a closed shell of electrons all in bonding orbitals and are exceptionally stable. Such systems are called aromatic. Analogous systems with 4n pi electrons are described as anti-aromatic. They are, well, more unstable than expected. Here is just a slide that shows you that planarity matters. I told you that benzene has 4 times 1 plus 2, 6 pi electrons. The next chemical should have 4 times 2 plus 2, that's 10 electrons. But we should not forget about planarity. So this chemical has 10 pi electrons, but it is not planar, so they do not overlap effectively, and we do not get aromaticity. This one, 18 aniline, is planar and it is aromatic. Yes. So 18, it's 18 minus 2, it's 16, divided by 2, it's 8. So it's 4 times 8, divided by 4 is 4. So 4 times 4 plus 2. Yes, please, I see a question.
Yeah, so how we can basically just simplify the about aromaticity. So what aromaticity it is, just one more time?
Well, for practical reasons, we will mostly meet with benzene. So if we can recognize benzene and we see that there are 6 pi electrons, that will mean that that chemical is aromatic. In chemical sense, aromaticity means that it is more stable than we can expect. So here's an example for you. So here is an alkene interacting with a bromine gas. You see that dibromo addition product is formed. But you will not get anything like that when interacting with benzene. So you can't do that. It just does, the reaction just does not go. This chemical is too stable for that. When we will talk about chemical mechanisms and so on, I think we will dive a little bit deeper how that works. But you should remember that aromaticity brings a little bit different chemistry into the picture. On the other hand, if we do that at certain conditions, so we have a catalyst like ferrum brom 3 and we have bromine gas, we can get mono-substituted product. So here is addition product. So bromine has added, destroying the double bond. But since aromaticity means much more stable compound, it means that this molecule does not want you to destroy the double bond. So it doesn't want to take bromine, just destroy one of its double bonds for the sake of attaching bromine. While in case of alkene, it happily does. And this is mono-substituted product, so you have kicked off one of the hydrogens and replaced it with bromine. And all double bonds are preserved, because they are not just double bonds, so these electrons are like smeared all over the ring. So it's very, very stable. Okay, I see more questions. Yes, please. Nope.
Jen, you have the hand. Where?
Well, I just wanted to, maybe it's the context, clarify about the pi bonding interactions in, so how did it differ from the sigma interactions?
Okay, let me return return back. Here you see this green thing. This is a sigma bond. It is between, so electron density is between two interacting atoms. So it is here, yeah? And this thing above and below is the pi bond. So there is some probability to find electrons above, some probability to find them below, but not here and not somewhere else. So here is the largest probability. So this thing is called pi bond, and this thing is called sigma bond. Pi bonds are created from atomic p bonds when they overlap sideways. So here you have a p bond of C atom. Here you have p bond of oxygen atom. They overlap sideways, and if they interact constructively, they create a pi bond. So that will be a bonding orbital. The other thing, the destructive interaction, give you anti-pi bond. Yes?
Oh, so sigma bond is destructible interaction.
No, sigma bond is constructive as well. So destructive interaction gets into anti-bonding orbital, and we designate them with stars. So this is sigma, and anti-bonding sigma we will designate as sigma star. Okay, let me return a bit more. We had this previously, I guess. So here you see, this is a pi bond. This is constructive interference. and this is bonding pi orbital. This is destructive interference, so that's how it looks like. Here it is. This is pi star, so this is destructive interference. Destructive interference has higher energy, so molecules will not like to create this type of things because it's not a bond. They want to go lower in energy. And let me find you somewhere sigma bond. No, this is still pi bond. And this is sigma bond, or maybe the first slide. Oh, let's take this one. And here is sigma bond. Here it is. And here is anti-bonding orbital, sigma star. So here how it looks like. So in this case you have electron density near atoms. Here you have electron density somewhere away. So of course it has some higher energy, it's not so energetically favorable, so electrons will tend to stay here.
Yes, so
Is it more or less intuitive for you?
I mean, all right.
Okay. I guess we will meet with them times to times, so probably can get a grasp of what is happening. Okay. Okay, we are almost done. This is just an example of different molecules that contain part that is aromatic. So these are heterocyclic aromatic compounds, and with the black color, you see the part that is aromatic. So it is flat. If you calculate its geometry, you will get something flat, and it has the right number of electrons to make all that aromaticity. So here is a primicarp. It's a selective insecticide which kills aphids but not ladybirds. So some sort of useful chemical. And here is the part that is that has exactly the aromaticity. So you see, once again, we have 1, 2, 3, 4, 5, 6 electrons that will take part in the pi bonds, and that will basically create that aromaticity. LSD, lysergic acid diethylamide. So it's that's infamous acid that's giving hallucinations and unfounded confidence in flying. So if someone flies out of the window, it may be due to overuse of the LSD. And once again, you see here different rings. Not all rings are aromatic. So once again, you remember, they should be flat and they should contain the right number of electrons. We'll meet these parts time to time, so probably it's not a big problem if you can't spot them on the fly. But anyway, that's the parts. If you calculate the number of electrons and so on, you will get the right number of electrons, and you will find out that they are aromatic. Some more chemicals. So omeprazole, it's anti-ulcer drug. Once more we have here an aromatic part, and this one. Viagra contains some rings that are aromatic and a ring that is not. Pretty okay. Here is some chemicals called coumarins. They basically smell like a new mown hay, and they are found in lavender here and there, and including some furanocoumarins isomers that you can find in Sosnovsky hawkweed. This is an invasive species in Ukraine, and it can severely damage skin. So if you see something like that, you better don't touch it. It interferes with the respiration system, and the ultraviolet from the sun starts damaging DNA and creates some nasty blisters, and that looks pretty pretty not good. Yes, I see the question, so let the questions be. And
Yeah, the last question. Can you return to, let's see, and the previous slide, please? Yeah,
yes,
this what when we talk about ME, what is that? It's methyl or
yes, that's methyl.
what is it?
That's
Because I didn't find it in the table.
oh, I will probably show that next time. So this is CH3. So that's
Yes,
methyl
it's a
methyl
methyl.
group. Yeah.
Yeah. Okay.
Okay. So I guess with that all being said, I'm pretty complete. So about the homework, I already told you.
Sorry,
So
sorry. I have a question
yes, please.
about bonding orbitals. So you told us that we will only consider higher energy orbitals when
Yes.
we will figure out the bonds. But what, like, will it work in every case? Because I'm curious about cases, for example, of cuprum.
Mm-hmm.
It's not really clear to me how there we will have this canceling out logic.
Um,
If it's like a special case when we don't have like full lower orbitals and then
uh,
yeah.
well, even in the case of copper, if it will combine with something, we will still consider only the highest orbitals, um, because the orbitals that are lower, if they combine with other lower orbitals, yes, they create new molecular orbitals, but they will be filled up. So even in case of copper, we just used the few highest orbitals, so some s orbital and a d orbital, but we didn't touch anything below. So we can probably just disregard everything below and consider only that two highest orbitals.
Okay, so only the ones that are not fully filled, right?
Um, oh, one more please. Once more please. I didn't hear.
Yeah, only considering the ones that are not fully filled, like is the case with copper that we consider only.
I know that it's a little bit strange definition, but let's say so. We consider only highest energetical orbitals where um, so-called valence electrons sit. So I know it's maybe not a good definition because I cannot define that strictly. Where do we draw that line exactly for each atom? But from practice, we will mostly use I know some carbon atoms, some nitrogen atoms, and we will be concerned with s and p orbitals, highest s and p orbitals. In case of copper, I know that there may be something quite complicated because D metals or some even F chemicals like lanthanoids or actinoids, they they can be quite complicated to describe, and there may be some effects I even don't know. So for
Okay,
our
thank you.
yeah, so for our purposes will be enough just some few highest orbitals. Maybe in some cases something exotic we will force to consider something else, but and I think there should always be some sort of threshold that you cut off and you say that I do not consider anything below this energy because it's not effective, everything is filled up with electrons, and whatever I get will be just, I don't know, bonding plus anti-bonding. Yes, please.
Yeah, one more question. Are we gonna do not do but like fulfill the field about CRISPR or Cas9
CRISPR-Cas.
about
Well,
this.
I
Yeah,
didn't plan, but I think I can look for adding it somewhere. So I'm still writing this course on the go. So if you want something about CRISPR-Cas, I can
it's
find a
quite
way to fit
new
it in.
because yeah, we all will work with some DNA or RNA, and CRISPR is quite new, like
Okay,
not new, but more in technology how to involve in that. So I think it can be interesting.
okay, I write it down, and I think I'll find some way to fit it in. Well, I guess
Yeah,
first
yeah.
5 lectures will be just more or less chemistry, but then we will get to molecular and let's say cellular level biochemistry. So why not? I guess it will fit somewhere in there. Good.
Yeah.
Okay. Any more questions? Yes, please.
No, probably not right now.
Okay.
Yeah,
Uh,
so
Good. If there are no more questions, I guess we can wrap up. So I basically told you everything I wanted. So homework you'll check later. So that's it.